I'm going to be working the problems from the Maclaurin series worksheet. It, used to be called classwork 4.7. By the time you're watching this, this might be homework 12.1. But generally, the instructions for the first side is write the first four non-zero terms and the general term for each of these functions. Okay, so we're going to start with one of our known Maclaurin series, e to the x, sine of x, cosine of x, 1 over 1 minus x. And we're going to do some of those manipulations on them. This is not the biggest worksheet, so I'm going to have to write small. So, x squared sine x. Okay, see, the one that I'm supposed to know is sine x. So I'm going to start off with sine x. First four non-zero terms. And the general term. That's not four non-zero terms. And the general term. So that would mean x squared sine x is going to be, well, I'm going to just multiply each of these things by x squared, because it's like I'm taking this whole thing and distributing it in x squared to each term. So x times x squared is x to the third minus x to the 5 over 3 factorial plus x to the 7 over 5 factorial minus x to the 7 over, no, that's going to be x squared times x to the 7 is x to the 9 over 7 factorial.
Oh, and I have
And the general term, I'm going to just basically multiply x to the 2n plus 1 by another x squared. And you can always write just x squared, x to the 2n plus 1, but since I know what that's going to be, I'm going to call that 2n plus 3. And the factorial number is unchanged. All right, the second one, cosine x minus 1 divided by x squared. Okay, I'm going to start with cosine x, then I'm going to subtract the 1, then I'm going to divide by x squared after that. So cosine x is equal to 1 minus x squared over 2 factorial. All even terms, because cosine's an even function. Know that it, when writing the general term, it alternates. It's got even powers and even factorial numbers in the denominator. Okay, so cosine x minus 1 would be what I would get if I just subtracted 1 and lost this thing. So what I'm going to do is I'm going to say, okay, well, cosine x minus 1 is going to be everything but this. And then if I divide by x squared, then I'll distribute in a 1 over x squared to all the terms. Okay, so that's gone. I've got negative x squared divided by 2 factorial, and then I'm going to divide by x squared, so I'm going to have 1 over 2 factorial plus x to the 4. If I had an x squared down in here, I'd have x to the 2, and really what's going to happen is it's going to reduce the power by 2 on each of these terms. Okay. Since they want 4 non-zero terms, I'm going to have to get another one, so it'd be plus, it would be x to the 8 over 8 factorial, but now it's going to be x to the 6 over 8 factorial because of reduction by 2. And pretty much the only thing that's happened to the general term is that the power's gotten reduced by 2, so I'm just going to call that x to the 2n minus 2 and divide by 2n factorial, because factorial numbers haven't changed. Okay, we know that starting with e to the x, e to the x is 1 plus x squared over 2 factorial, x to the 3 over 3 factorial, up to x to the n over n factorial. E to the 3x, I guess I'll do this in 2 steps. e to the 3x is 1 plus 3x plus 3x squared divided by 2 factorial up to 3x taken to the nth power divided by n factorial. So 5 e to the 3x would be if I just multiplied everything by 5. So it would be 5 plus 5 times 3x plus 5 times 3x squared divided by 2 factorial. And then 5 times 3x to the nth power over n factorial. Now, this is definitely one you could call like, you could say it's 15, you could say it's 5 times 9 is 45, but then do you know what 27 times 5 is? I don't, so maybe 115, maybe not, no, maybe 140, who even knows? Okay, so I'm just going to leave it like that, right? You could call this 5 times 3 to the n x to the n over n factorial, or you could not, it really doesn't matter. Cosine of x to the third. You start off with the one you know. And then wherever I see x, I'm replacing it with x to the third. Okay, I'm replacing x with x to the third. Okay, you could call this x to the 6n if you wanted, or if you didn't want, that would be fine too. Okay, for this one, I'm going to have to adjust this thing a little bit. Okay, start with sine x. Going to divide each term by x, because really what I'm doing is I'm taking this whole thing and I'm multiplying by 1 over x, which would distribute into each of the terms of the polynomial. So, and maybe I'll just write it like 1 over x times sine x is going to be 1, and then each time I'm going to have an x in the denominator, which will reduce the power by 1. Okay, so I had x to the 7, I'm dividing by x, that's x to the 6. Okay, I had 2n plus 1, but I lost 1 each time, so I'm just going to say x to the 2n, divide by 2n plus 1 factorial. And if you're looking at this, you're like, oh man, I'm not sure if this is right. What you could do is you could look and see, is the power always 1 less than the factorial number? And it is, if you look at it. E to the x minus 1 divided by x. This one we'll start with e to the x. I'm going to subtract the 1, so this will be gone, and then I'll divide by x. So So that thing's gone. I'm going to take all of these terms and I'm going to divide them by x. And so x divided by x is 1. X squared divided by x is x. X to the 3 divided by x is x to the 2. And from each term I'm losing 1 power of x, and the factorial number stayed the same. Okay, x cubed e to the x. Okay, it'd be pretty similar. We're going to start with e to the x. And at this point inside of this worksheet, and you're relatively new to it, you know, I was feeling a little annoyed. I'm having to write out the Maclaurin series for sine and cosine and e to the x over and over and over again. But really, that's what you need at your level where you're at right now. You have to know these things. Okay, everyone knows that. You just have to know them. And the best way to know them is just write them down a million times. So this is actually probably good practice. So x to the 3 times e to the x is going to be where I take this whole thing and I multiply it by x to the 3, which will kind of like imply some sort of distribution to all the terms. So x to the 3 plus x to the 3 times x is x to the 4. X to the 3 times x to the 2 is x to the 5. X to the 3 times x to the 3 is x to the 6. And then each time really I'm multiplying by x to the 3, so you could write it as x to the 3, x to the n. But you could also write that as x to the n plus 3. It really doesn't matter. It's the same thing. Okay, we're going to talk about sine of 2x. Okay, start with sine x. And sine of 2x, I'm just going to replace all these x's with 2x. And if you're doing this and you're like, couldn't I just like take this and use my eraser and clear out the x's and replace them with a 2x in parentheses? Like, yes, definitely you can do that. I think that's a very valid strategy. I'm just doing this to be most clear. So sine of 2x is where I'm going to replace x with 2x. And I've noticed this year that I've had some people being not as judicious as they should be with parentheses. This is definitely a case where we have to replace x with 2x in parentheses, because 2x to the 3 is not the same necessarily as 2x with parentheses taken to the third power. Right, because if you take this, multiply this by itself 3 times, you're going to have 3 copies of 2 and 3 copies of x. So it would be 8x to the 3. And it's all good because, like, I know what 2 to the 5 is, but, you know, it would take me quite a while to think about 2 to the 7, and that's a place where a person could potentially make an error, so I'm just going to leave it as 2x with parentheses to the 7. And then negative 1 to the n, 2x to the 2n plus 1 over 2n plus 1 factorial. Yeah. X cosine of 2x. Okay, so it's going to be very similar to this one, except then after I substitute the 2x, then I'm going to distribute it in x. And this is one that I really do prefer to leave, like, you know, without simplification. So I'm going to do that. So okay, cosine of 2x, I'm just replacing x with 2x. And then x cosine of 2x. It's going to be, I'm going to multiply each thing by x. So x minus x times 2x to the 2 factorial. X 2x to the 4 over 4 factorial. X 2x to the 6 over 6 factorial. Negative 1 to the n. There's that x I multiplied in here to everything. And there's 2x to the 2n from up here, and a 2n factorial in the denominator. I do prefer to put parentheses around the 2n factorial. I don't think that's the type of thing you'd get counted off for in the free response, but it is the most clear because, right, like, are you doubling the n before taking the factorial, or are you factorialing and then doubling? Okay. If you put the parentheses on, you're very clear you're going to double and then take the factorial of that doubled number. All right, sine of x squared. Sine's an odd function. It's got odd numbers in its Maclaurin series. It alternates. The powers of x are odd. The factorial numbers are odd. Okay, so sine of x squared be where I just replace x with x squared. So it's x squared minus x squared to the 3rd power, x squared to the 5th power. If you want to call this x to the 2, x to the 6, x to the 10, x to the 14, you can do that. It's fine. I'm probably not going to. Which would make that x to the 4n plus 2. If you think about it, 2, 6, 10, 14, that's 4n plus 2. Divided by this 2n plus 1 factorial number. All right, we're closing in on the end of this front side. It's been kind of a grind. F of x equals e to the negative x squared. So I start with e to the x. Squared. What I'm going to do is I'm just going to replace this x with negative x squared everywhere I see it. Plus, okay, so I'm going to take negative x squared to the nth power over n factorial. And just because we're getting to the point where we're about to flip over to the backside and have to do the reverse of this, you're not going to see them looking like this. Okay, they're going to be simplified. So what I am going to do is I'm going to actually say that's 1 minus x squared. Okay, when I square, it's going to still be positive. X to the 4 over 2 factorial. But when I take the negative 1 to the 3rd power or any odd power, it'll be negative. So I'll have negative x to the 6 over 3 factorial plus plus, okay, when I have that negative to the n power, that's negative 1 to the n times x to the 2n over n factorial. And then lastly, we've got x cubed cosine of x. And yeah, I forgot that it alternates, so I guess I'll just put a negative 1 to the n over there. That's not exactly how I would usually write it, but since I forgot it, I didn't have room over here. That's just the best I got. Okay, x to the 3 cosine of x is going to be just distributing an x to the 3 to all the terms, which will functionally increase the power by 3, as opposed to here when I substituted with x squared, it doubled all the powers. Okay, so that'll be important when we flip over the back side. So x to the 3 minus x to the 5 over 2 factorial plus x to the 7 over 4 factorial minus x to the 9 over 6 factorial. Negative 1 to the n, x to the, I increased the power by 3, the factorial number stayed the same. Okay. So notice how if it's still increasing by 2, like cosine normally would, it's going to be just something like on the outside. But if all of the powers are doubled, that's going to be something different. It's going to be substitution on the inside. On the back side, identify the function represented by each of the following series. Express each series in summation form. Okay, I think what I'm going to do is I'm going to actually, I don't know, I might do this, the summation form first and then identify, because sometimes it might be easier that way. But the first thing you're going to do, kind of the first decision to make is, which is kind of your base function that you're going to be working off of. And I think these first two are two really good examples. Okay, the one where you have all the factorial numbers and it's not alternating is going to be related to e to the x, right? Okay, and then the one that has alternating parts and has only odd numbers in the factorial, that's going to be related to sine x. Okay, because sine's an odd function, and we know that. We know the Maclaurin series for it has only odd numbers. So I'm going to do is I'm going to say, well, e to the x is 1 plus x. So it looks like I multiplied the 1 and the x by x squared. So my hypothesis is x squared e to the x. And I'm just going to think, is each power 2 more than I would expect? And for e to the x, it's x to the n over n factorial, same power as factorial number. And I'm seeing an increase of 2, so that would make sense with this. Okay, so that actually is making sense to me. So I'm going to write this as the sum as n runs from 0 up to infinity, because all of these Maclaurin series start at n equals 0, of, well, it would be x to the n over n factorial, but I'm multiplied by x squared, so it's x to the n plus 2, right? Because I've just increased the power by 2 each time. I guess I'm going to say that's equal. All right, this one clearly related to sine of x, right? X minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. And I'm seeing the same powers. So really, either what's happening is I'm just keeping on multiplying by a constant number to each term, or I've replaced x with something like 2x or 3x or 4x or 5x, or some number of x's. So remember that sine starts x to the 3 over 3 factorial. So I feel like this is just going to be sine of 3x, because I've replaced x with 3x here, and if I take 3x and I take that to the third power, I'll have 3 powers of 3 and 3 powers of x. Let's see, is 3 to the 5 equal to 243? 3 to the 4 is 81, so yeah, I guess that would make sense. So yeah, it's looking right to me. So this is the sum as n runs from 0 to infinity of, well, normally it would be x to the 2n plus 1 over 2n plus 1 factorial. And we are still seeing those same x to the 2n plus 1 factorials, but we're also seeing a 3 to the same power. So you could either call it 3x like that, or I could call it 3 to the 2n plus 1 x to the 2n plus 1 over 2n plus 1 factorial. It's the exact same thing. Okay. This is definitely going to be related to e to the x. E to the x is x plus x squared over 2 factorial. So all the powers have been reduced by 1. So I think I'm just going to say I took it and I divided each term by x. Okay, and that's e to the x. E to the x, if I had an x down here, I could write it like that. Or I could just say I've reduced the power by 1. Okay, this is going to be related to cosine because I'm seeing the even numbers, I'm seeing it alternating. And I know I don't have anything multiplied because I've got this 1 here, right? And cosine starts at 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. So, and this one seems a little tricky because like 16, 12, 18, 24, I'm doubling each, or I'm increasing by 6 each time. So it's like, what am I going to do here? And so what I might say is, you know, how did I get from what it's supposed to be to what I have? So I'm just going to work on the first 3 terms. And it looks like what I'm doing is I'm tripling the exponent. Okay. And then that would make sense that if what I was doing was actually, instead of taking x squared to the 3rd power, I was taking x to the 3 to the 2 power and x to the 3 to the 4 power, right? Because that's how the, x power of a power works. We're going to multiply the exponents, and 2 times 3 is the same as 3 times 2. So I'm going to say that this is probably cosine of x to the 3. So that would mean that the, power 8 term would be x to the 3 to the 8 over 8 factorial, and that is x to the 24 over 8. So I'm going to say that's cosine of x to the 3. And then that would make sense because it wouldn't change the 1 because there was no x in there in the first place to replace with x to the 3rd. And so since the power is just 3 times as much as we expect it to be, I'm going to just call it x to the 2n times 3, which is x to the 6n divided by 2n factorial. And then just as a quick check, is the factorial number 1/3 of the power? Yes, 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 yes. Okay. I'm seeing the odd numbers, I'm seeing the alternating sign related to sine of x. I'm seeing this 3 multiplied into all the terms, so it's probably going to be related to 3 sine x. But there's something off with the powers, right? The powers are not quite as big as they should be. They're less by 1. So really what I'm doing is I'm just dividing by x, I guess. And remember I had sine of x over x on the front side, so I'm going to just make sure I've got x to the 2 over 3 factorial, x to the 4 over 5 factorial. Where was that? X to the 2 over 3 factorial, x to the 4 over 5 factorial. Yeah, that's looking right. And then I'm going to write it in summation notation. I'm going to say, I call this, well, I've got a 3 on all the terms. I've got an x. For sine, I should have an x to the 2n plus 1, but I've reduced the power by 1, so I just end up with an x to the 2n over 2n plus 1 factorial. Okay. 1 minus x squared plus x to the 4 over 2 factorial minus x to the 6 over 3 factorial. Okay, this one... because it's alternating and it's got all of them. So I feel like this is going to be, if it's alternating but it's got all of them, it's got a really good chance of being related to e to the negative x. Okay, so, and yeah, it looks like, because I've got this like 0th term divided by 0 factorial, first term divided by 1 factorial. Is this going to be e to the negative x squared? Wait, I know I did e to the negative x squared on the front side, so let's just look. 1 minus x squared plus x to the 4 over 2 factorial minus x to the 6 over 3 factorial, where the factorial number is half the exponent. Yeah, this is e to the negative x squared. Okay, that one's pretty tricky. Really what you know is And you might be thinking, like, well, what if it was like sine of x plus cosine of x? And I would see what you're saying, but then, we're missing the odd power terms. We have the odd factorial numbers, but all the odd factorial numbers are negative. And if we were seeing sine of x plus cosine of x, we'd see like two positive and then 2 negative and then 2 positive and then 2 negative. They kind of go in groups of 2. So this is the sum as n runs from 0 up to infinity of, okay, well, it's alternating. It's x to the 2n divided by n factorial, right? Because the power is twice the factorial number. Okay, this is going to be related to cosine for sure. And so whereas I'm expecting 1 minus x squared over 2 factorial plus x to the 4, it's always just 3 bigger than I'm expecting x to the 6 over 6 factorial. It's just 3 bigger. So I think that this is going to be not replacing x with x to the 3, because then it would be 3 times as big, not just bigger by 3. So I think I'm going to just be multiplying by x to the 3 cosine x. And that would make sense because this is supposed to be a 1, and I've just I've multiplied it by x to the 3. I wouldn't replace anything if it was just like cosine of x to the 3. There'd still be that 1. And you see that like on number 4 up here, it was cosine of x to the 3, and we didn't replace on the 1. And I'm going to cook up a general rule. I'll have, it's alternating. I would normally have x to the 2n over 2n factorial, but I've increased the powers by 3, so it would be 2n plus 3, 2n factorial. Right. And there's this other problem that I'm not really sure why it's on this worksheet, but it's never a bad time to practice this. It's a pretty common type of question. Okay. We know that we've got, I should put parentheses there. We know we've got a Taylor series. We've got it written out in summation notation. And we know that the series converges at x equals 7. Well, we also know that the Taylor series is centered at x equals 4. So as far as this is kind of like an interval of convergence question, no matter what, I can promise you that this series is going to converge at x equals 4, because if x is equal to 4, regardless of the nature of the derivatives, you're going to just be adding up a bunch of zeros. Okay. They're saying the series converges at x equals 7. Now they said this worksheet is pretty old, and I've been using this one as long as I've been doing Cal BC. And when I first started, we didn't have to worry about absolute and conditional convergence. So it was either just converges or diverges. That was the end of the story. So they're not going to tell you. They're just going to say it converges at x equals 7. We don't know. If they had said it converged conditionally, I would know that the interval ended here. But just knowing that it converges, this could be an endpoint or it could not be an endpoint. So I know the radius is at least 3. That's why they're offering us the option of unknown, convergence, divergence, unknown. Okay. So this is certainly going to converge. Anything between 4 and 7 or between 1 and 4 will definitely converge. So that's x equals 2, definitely converges. At x equals 1, this is 3 units away. If the radius is 3, there's sometimes where it'll converge here and diverge here. There's sometimes where it'll converge at both endpoints. There's times it'll diverge at both endpoints. We don't know that this is an endpoint, but we also don't know that it's not an endpoint. So this is unknown. Okay, and this one's also going to be unknown. Okay. If they had said the series converges conditionally at x equals 7, then we would have known that this was for sure an endpoint, and anything beyond it, like x equals 8, would have given us divergence. All right, that's all for that worksheet.